Hi everyone, welcome back to Causality with Boris, broadcast from Sobolev Spaces. In this video, I talk about attributable proportions, and I will start with a little excursion into the history of epidemiology, and then I contrast proportions and ratios. Watch to the end to see that the attributable proportion is really a proportion, not a ratio. There will be additional material attached to this video. Click on the link in the description and it will be sent to your inbox. The primary method of health research is to examine differences between treatment groups. Our goal is to explain differences in outcomes by group membership. In observational studies, we have no control over treatment assignment. Treatments are observed. And it's quite possible that the determinants of outcomes may be distributed differently in treatment groups. If they differ by outcome determinants, we suspect that difference in outcomes reflects the effect of those determinants. The causal analysis contrasts two hypothetical scenarios, all treated and all untreated in the same population. We're looking at the potential outcomes of treatment alternatives. The treatment effect, then, is the risk difference between the treated and untreated population. We are comparing two hypothetical risks. But many policymakers look at existing and hypothetical risks. They are trying to figure out how much current risk can be reduced by eliminating exposure in the existing population. How many injuries could be prevented if everyone buckles up? How many repeat procedures could be avoided if all patients undergo bypass surgery? In doing so, they compare hypothetical population to a population with existing risk patterns. Epidemiologists invented stratification. They also figured out how to use it to inform policy. And I'm talking about attributable fraction. Levin first introduced attributable fractions in 1953. Then in 1988, Greenland and Robbins argued that in a cohort study, attributable fraction shows an excess of diseases that can be attributed to exposure. Today, the attributable fraction for population generally refers to the proportional change in the average risk of disease when exposure is removed from the population. The distribution of other risk factors deemed unchanged. Typically, epidemiological measures need adjustment. We are concerned that other factors may influence disease occurrence. The attributable fraction also needs an adjustment formula, and the screen shows it. We compare the observed risk to the counterfactual risk in the same population. The first is simply the average of observed outcomes. It contains both exposed and unexposed units. The second is the average of counterfactual probability of disease in the absence of exposure, and its average over strata of other factors. These other factors remain unchanged. In this thought experiment, we consider existing and hypothetical populations. We look at risk reduction by eliminating exposure altogether. We compare the observed average risk, we denote it E of y, and the counterfactual risk E of y naught. The counterfactual risk combines the existing risk pattern associated with other cofactors. These are condition variables essentially. The risk is determined by the adjustment formula. We average existing disease risk over strata of conditioning variables, the usual stratification. Ideally, we find the existing risks using the sample means from strata. We then average them over strata prevalence. If data are limited, we estimate risks using regression analysis. We fit a model, find regression coefficients for exposure and covariates, then we set the exposure variable to 0 and estimate the conditional probability of disease for each covariate pattern in the population. That means we find the outcome probability for all members of the study population. That means we calculate their unexposed risks, regardless of their exposure history. The sum of the unexposed risks averaged over strata is the counterfactual marginal risk, as if the exposure were removed from the population. This formula divides the difference between observed and counterfactual risk by the observed risk. Although called fraction, it's not a fraction. It's not a proportion. Proportions describe the part in relation to the whole. Simply put, denominator must include numerator. When two numbers refer to different quantities and neither is included in the other, they are ratios, not proportions. We intuitively understand proportions when we talk about diets. We say that carbs should make up less than 50% of daily diet, and their ratio to fats should be 2 to 1. The first is the proportion, and the second is the ratio. Population is a target of our inferences. We look at excess risk in relation to the risk in the exposed. Excess risk is the risk difference between exposed and unexposed populations. So, two counterfactual populations, all exposed and all unexposed. The risk difference is the difference between the two counterfactual risks. We divide the excess risk by the risk in the exposed population. Epidemiologists are often interested in the reduction in disease relative to existing exposure pattern. This indicator is known as attributable fraction for the population. Expressed as a number of cases, it's called attributable caseload. It estimates the reduction in currently observed cases if the population would be completely unexposed. We compare the observed and counterfactual risks. Attributable caseload is a useful public health measure. We predict the impact of intervention that would make all people in the population unexposed to harm. Historic examples are car emission control, seat belts, mass vaccination uses the same logic. Let's show it's not a proportion. First, some notation. Let's X denote binary exposure. It encodes exposure as 1 and non-exposure as 0. Then Yx of u is potential outcome if the exposure is set to the level x for unit u. For each u, there will be two potential outcomes, y1 of u and y0 of u, when unit u was exposed and non-exposed respectively. The average of potential outcomes are counterfactual marginal risks. We think of marginal risk as the proportion of the population that develops outcome if all units receive the same exposure. The relative excess risk, then, is the difference between the marginal risk in exposed and unexposed, P1 minus P0, divided by P1. On the other hand, the attributable caseload includes the observed outcome probability. We take the difference between the observed risk and the marginal P0 and divide it by the observed risk. You may notice that numerator is not part of the denominator here, and its values ranges from -infinity to 1. Again, numerator is not part of the denominator. Policymakers often project the reduction in risk if the harm is eliminated. They compare the observed risk to the counterfactual risk. They are comparing what is with what isn't there. In his paper published in 2012, Suzuki cites all known measures that compare the two risks, and he says that the attributable proportion is the best measure, because it's the true proportion. Numerator is part of denominator. Suzuki distinguishes the attributable caseload from the attributable proportion with a simple rule. Proportion has numerator as part of denominator. Let's see it. As usual, I let y denote outcome and x denote treatment. Then we need a potential outcome. After all, we are looking at counterfactual risks. Let ya be a binary outcome in which the binary treatment x is forced to take the value a in all units of the study population. So, for example, y0 is the potential outcome in the absence of treatment. The attributable proportion describes observed outcomes that would not have occurred if the population had not received treatment. To find it, we subtract the joint probability for the observed and potential outcomes from the observed outcome risk. Then we divide it by the observed risk. This is true proportion. Denominator includes numerator, and its value varies from 0 to 1. To see this, we simply present the outcome probability as a sum of two joint probabilities. One is for observed and potential outcomes in the untreated, and the other is that for the treated. The sum in denominator includes numerator. This proportion describes the risk reduction for the current, not a hypothetical population. It compares the world as is to the world as it might be. This is what Pearl calls the probability of disablement. The probability that the absence of event X is 1 prevents event Y is 1 when we observe that Y is 1 actually occurred. Consider patients who died few years after treatment for heart disease, whether by angioplasty or by surgery, and ask how many deaths would be avoided if they all had surgery. This measures the proportion of patients who would have survived if they had surgery. Here's the main message. Excess risks compare counterfactual populations. Everyone receiving treatment versus no one receiving it. Attributable proportions compare a counterfactual population to a population with existing exposure and risk patterns. The key idea here is that we use the existing risk patterns to find counterfactual risks. You've watched another episode of Causality with Boris. Keep on watching.